And so that's basically a summary of the practices. I'm going to go through this procedure with you, what we've done with our students. And again, this is where I'm thinking that might be, these are all opportunities that you can do with your students, and I'll key in a little more specifically on some of those now. So there's a whole process that we have students do in one of our classes where they actually interact with a town they have some requirements because of state stormwater regulations. So we're helping out the towns to identify where good retrofits might exist or good retrofit opportunities might exist. So we go through this whole process in class. Today, I'd like to step you through these first three here, and we might get into this second one if we have some time and you're interested in doing the rain garden sizing and a little more about that. All right, so when it comes to assessing your site, it all boils down to thinking about where the water is going. And despite the fact that it might not be as pleasant to be outside when it's raining like today, it's actually a great day to look around and see, okay, is the water that's falling on this roof going into a pipe somewhere? Is it running onto the lawn, but then it's all compacted, so that's running down to the pond? Is it in a catch basin, which goes into a pipe that goes right out to the pond? It's a great time to see that. So this directly connected question is an important one, because we might have a parking lot that drains to a grass swale like this, where that water will have a chance to infiltrate. Or we might most likely would have parking lots at schools that drain into some sort of catch basin structure like this, where that water goes into a pipe and is out of sight, out of mind, and it goes out to the nearest water body. So if that's the case, your rooftop, your driveway, your road, it's all directly connected to that local water. So whatever gets applied to that road, misapplication of fertilizer, road salts, everything. So what kind of sparrow do we have here? Who's a good bird person? The song sparrow, was it? House sparrow. All right. So one of the first things we do with the students, there's the benefits of the technology now. It's very easy to use Google imagery to see what's going on the site before we even make a physical trip out there. So hopefully this works. We'll do the quick demo for you here. All right, so here we are on the UConn campus. I'm gonna zoom in near the UConn Dairy Bar. How many people have been to the Dairy Bar? It's a great place, yes, all right. So I've chosen this site because first of all, it's near where we put this rain garden in, but it's a great opportunity to see what you would likely see at your school. So when I zoom in just on the aerial imagery here, what do I see for these buildings here? I see a lot of flat roofs, which is very common for schools too. Flat roofs, they're easy to install, and the downside to them, however, is that most of them have internal drainage that you cannot really touch. So there's no way to disconnect that rooftop from that pipe system. So I can see we've got a flat roof here. What I don't know is if there's a gutter downspout or not. I've got some other flat roofs over here too. So in the old days, that would be about what we could see. But fortunately now we have Street View, which we can drop our little friend wherever we'd like here. And now we can pan around and confirm, okay, I was right. There's only a gutter downspout on this little tiny section of roof. The vast majority of this building has a flat roof with internal drainage that I can't do anything about. So I can pan all the way around. Sometimes the schools are limited, depending on how close you are to the road. Because of security issues, they don't put a lot of photographs around schools, understandably so. But you'd be surprised. Sometimes you can still see a fair amount. So let's take a look then a little further over. So there's the Dairy Bar itself. That building also, flat roof. I'd see no downspouts on the outside to potentially disconnect. However, if we get over to this newer building here, aha, finally, I see some downspouts. Let's get a little closer. All right, so I got two downspouts there. I've got a downspout from that big section of that upper roof. So that's good news. So I would, with our students then, we would then flag this as a site to potentially visit and mark it down so that when we go out to the school, we know that we're going to key in on this one. But I'm going to leave the street view, and I'm going to show you what we would then do when we came back. So after we would visit it in the field, and we would say, okay, this is a good site, I would then have the students measure the watershed area of that rain garden site. So for a rooftop, it's easy. I could see that that downspout that drains this triangular section and this lower section are what drains to that site. So if I right-click on this with my mouse and do measure distance, in addition to measuring distance, if you complete the shape, it'll measure the area. So if you know about this, sorry for repeating it, but if you look at it down there, we got 900 square feet in that roof. Do this lower section here. This is right in Google Maps. Anybody can do this. Yep. This lower section is 1,300. So around 2,200 square feet total of drainage area. So we would then use that number to calculate the size of the rain garden, which we may get to here a little later. All right, so this is just an example for you, something you could do with your students. For parking lots, it gets a little more complicated. And we typically have to use topo lines or topographic lines to help figure out where the water's draining in a parking lot. Sometimes it's obvious if you've got a giant lot that slopes down to one end, it's pretty easy. But other times it can be challenging to figure out what the actual drainage area is. So if you're doing this on your site, once you've got those topo lines, I'll show you this in a second, but generally it's handy to bring a hard copy with you outside. We tell the students this like 5 times, but they still like to try to do it on their phone. And I mean, I know they do everything on their phones these days, but a clipboard and a piece of paper, when you're looking at topographic lines and trying to delineate a watershed, is really the best tool. So this is what we do. We have them out there with a clipboard trying to figure out what is the area of this particular parking lot, perhaps that drains to this catch basin, because we identified this area as a good rain garden opportunity. So as I said, schools can be challenging because of those flat roofs. And if the downspouts exist, that can be a good opportunity. So that's what I will key in on here. This is one example of a project that we were working on last summer. This is down in New Canaan. So here's a flat roof, but that section had downspouts. So our students identified this as a good place to install a potential rain garden in this little grass area here. In the parking lots themselves, this can also be a challenge because of the way that they've been designed. So typically they're designed with curbs and catch basins. The lots are sometimes sloped to the middle where there might be a catch basin, and it's very difficult to get that water away from that section without a major excavation on that lot. So we try to find areas for schools that are an easy retrofit. So using permeable pavements is, someone might say, okay, yeah, just put in permeable pavement everywhere. Doing that as a retrofit is very expensive and not practical for most schools. However, we also talk with the towns when we're doing this and ask them, do you have any planned projects coming up? Like if they know they're going to be redoing this lot, that might be a nice opportunity because it's an easy, small cost differential then, rather than doing it out of the blue with no other work going on. So this is an example of another site in New Canaan. So you can see these topographic lines here. So the students identified this blue area is the watershed of this little island that they could potentially direct some runoff into. So here's a close-up of it. So water right now is going into this catch basin from that drainage area. But we would propose, and actually they're likely going to be installing this one this summer. They would remove the curb in a small section on each side of this catch basin and dig out this grass section so it's depressed, plant it, and now you've got an easy rain garden retrofit. We also have the students do these calculations and show them for the town so they can quantify that benefit, the annual gallons treated, the amount of phosphorus and nitrogen removed too. So here's another tool for you. This is something that some of my colleagues at the Center for Land Use Education and Research have put together. So this is in a collaboration with DEEP. So posting all the environmental data that are available on a website. So this is cteco.org. www.uconn.edu. There's a lot of data on here that you can use. I'm going to show you just one small thing, but on this viewer, you'll see there are a lot of options that you can do here. So we just say OK. I'm going to bring us into the UConn campus. So you can put your address in there. Now, over on the right-hand side are where all your options are. So you can, there's information on individual parcels that are there. What I'm interested in right now are the contours. So we're going to turn those on. So contours connect, if you're not familiar with these connect lines of equal elevation. So without any imagery, it's tough to tell what's going on there. So if you scroll down a little further, you can turn on some imagery. Statewide imagery is right here. And there we have some very high quality imagery for you. So now we get to see, okay, we have topographic lines. So if you're familiar with this, this is easy. You know that these heavy lines, so this, for example, is 710 feet. Each of these lines is a 1 foot contour. The next heavy line is down here. So this one is 700 feet. So 701, 702, 703, 4, 5, 6, 7, 8, 9, 10. All right? So across this parking lot, you can see, well, let me ask you, which way would water be moving on this parking lot? In which direction? From top right to bottom left. Correct. So water moves in relation to gravity, just like everything here, on the surface and subsurface. For delineating a watershed, typically the old way we would do this with a watershed, or with an actual stream watershed, you move and you delineate the boundary of that watershed moving perpendicular to the contour lines until you get to a high point around that stream, in which case the water on the other side would go to another watershed. It's the same idea with a parking lot, it's just a smaller scale. So this is where the data are, and I think this is where I have for you, if you would like, an opportunity to delineate the watershed of the catch basin that's under this star. So on the paper that I have for you here. So this is for you. I have copies if you'd like to take a crack at this, pair up with someone. Sure. Thanks, Jane. Let's just keep one. If you would like to zoom in on this site, whoops. The QR code that's here on the paper or on the screen will bring you right to that map, a Google map on that site. So if you'd like to measure the area, you can do that. I'll give you a couple minutes to give it a try, and I'll walk around and answer questions if you have them. So one of the points of this exercise was that it's more complicated than it seems at first glance. And it definitely is. And that's the case for a complicated watershed of a stream too. So doing this with a topo map for a stream is actually really challenging. But for this, the main thing to think about, and this is what I tell the students with this, think like a drop of rain. So if a drop of rain fell right here, for example, it's going to move perpendicular to the contour line and not go into that catch basin. So you know the boundary has to be somewhere this way. So this is the boundary that I delineated here. So the edge of this curved island, we would go perpendicular to these contours up here, all the way up till it meets the next curb. We're ignoring the grass for now. So then it's easy, it just follows the curb. What you don't know over here is where it comes in. So I usually would then go down to this point, go perpendicular off of that, and then that closes it. So if a drop of rain fell here, it's going to move down, and go out into the road and into another catch basin. That's a separate watershed. So this is the boundary of this particular catch basin. And this is exactly something that we would do for these towns because we need to figure out how big it is to know how to size the rain garden. So the area of this I calculated, and I'll show you how to do this. You can do it on Google Maps. The downside is you have to guesstimate based on your drawing there and translate it over to Google Maps with that area measure tool. About 23,000 square feet. So here's the calculation. This is something useful for the students if you'd like to have them figure out how many gallons are going to come off of that watershed. So 1 inch of rain. I'm going to send an homage to my high school chemistry teacher who told me this unit conversion method, which I still use to this day and teach my students. So that we just use equivalents here. 1 foot equivalent to 12 inches, 7.481 gallons in 1 cubic foot. So our units cancel, inches cancel, square feet times feet is cubic feet. That cancels. And we get 24,142 gallons. So if you wanted to do the average year like I did for this site, you just multiply that by 48. So this is just a simple example of how you can do that kind of calculation. So I'm going to go pop back into CT Eco for a second and show you in there. So in this viewer, there's a tool on the left. Right here, it's measurement. So you select area right here. And this allows you to draw a shape and it will tell you the area. So you can click on the shape. Again, going perpendicular to those contour lines. So there you go. You can see, get the idea. About 24,000 square feet. Okay? Any questions on that? I know this isn't the ideal environment to be doing this. You may not have your computer or anything. Go ahead. If you're doing it it's hard to do it on the phone. So Google Maps is much easier on a laptop, yes, but there is a way to convert it in there, or you may just have to do that conversion yourself afterwards. But yeah, if you're on the laptop, it defaults to square feet. Any other questions? Yeah.
Do you usually, for a project like this, want to assume that the water landing on the grassy area here will not come down to the paved area? What are your assumptions there?
So the question was, do you usually assume that that grass area does not drain onto the grass? And it's a good question, and that's something we would need to verify in the field. So that's why we always do a field visit with the students for these particular kinds of projects. Because if that does drain on, it's not going to contribute as much water as the parking lot would, but depending on the condition of it, it might contribute a fair amount. So there's another calculation that we can use that factors in that grass area. Good question. Okay. So we were here. Okay. So these are resources for you. During COVID, when we couldn't get outside with the students, we made some videos showing them how to do this watershed delineation in like a parking lot. So this is all just little short YouTube videos that you can use just to see the technique. All right. So again, these are all resources for you. This is just a few shots of us with the students out in the field. So we spend a lot of time looking down catch basins, seeing where pipes go. This is part of the process when we're out doing that. So potential activities that you can do. So we talked about at the beginning, looking up the water quality report for a local stream. That's using How's My Waterway. Delineate the watershed of the stream using stream stats. We're not going to torture them with the manual method like we had to do in the old days. Calculate an event and an annual runoff volume number, which I just showed you how to do in there. So there's also a way to calculate the pollutant export, so the nitrogen and phosphorus that might be expected to run off of that site. At the end of this presentation, I've got a few slides that we use. It's basically like a cookbook recipe for our students as to how to do that for your site. I'm not going to go through that now because it's dreadfully boring, but it's a resource there for you if you'd like it. You can help have the students identify a potential retrofit at the school. So rain garden, green roof, maybe. Green roofs, everybody likes the green roofs. I love the green roofs too. You got to have the right site for one though. So it would be, most of the roofs you don't have access to, you can't see it. You have to also know if it can support the extra weight. So there's some engineering that needs to go in ahead of time. So usually the green roofs end up best on like a patio or something because they come in trays. They can easily be added to a patio. It's a good educational opportunity too, but it costs money. So somebody's got to pay for that. So, but the students can calculate those volume reduction potentials. So rain gardens typically reduce about 80 to 90% of the volume that that runs off into them. And then lastly, calculate the size of the rain garden and potential plants that you might install in the garden. So to wrap up this section, there are many considerations if you want to install GSI at your school. There's multiple benefits from water quality, wildlife habitat, educational opportunities. Obviously, that's why you're here. But as a caveat, not every site is appropriate for every practice. We've had a lot of people come to us from schools and say, we want to put a rain garden in here. Sometimes there's just not a good site for it. And maintenance is critical to the long-term success of these. These are some other, question?
Could you talk about how many towns and municipalities have changed their regulations to require this sort of language in the Wetlands Act and everything, and the fact that young people, if they are trying to do this, they have to go to the local commissions to make sure that they have to look at that as part of their rules.
This is a very good question, and I'm going to get to it in just a second. So these are some other links for you for references with your students. We have a rain garden website, and there's also, we've created a mobile version as an app at this point. So it's rgapp.nemo.uconn.edu. If we have time, I'll show you that. The program where you saw the students out in the field, that's what we call our Stormwater Core training program. So we teach a classroom class, and then we have a follow-up practicum semester where they do these projects with the town. Our MS4 site is where we've provided educational and other resources for towns that are subject to the state stormwater regulations. So this was a project that we had funded through Connecticut DEEP, and there's information on here about which towns have changed their regulations related to this stuff. What was your name?
Karen Nelson.
Karen. Karen asked a very good question about towns and which ones have changed their regulations, because that's where this stuff really happens. And the students need to understand that. And it's a great opportunity for them. We've also, on the CLEAR website, which is here, there's a separate project that we did that shows which towns have changed their regulations. So there's a map you can look at that shows that.
And students have the right, it's not just the white hairs that can require their land use commissions to make those modifications.
Students can request that their land use commissions make those changes. If they're a resident of that town, that's correct. That's right. This last one here is a rain garden training certificate course that we put online. So we were doing this training, COVID hit, so we basically turned it into an online module system. So there's 7, I think, modules in there. It takes 3 to 4 hours to go through, and then you can get a certificate. So that is might be useful for students or teachers that are interested in this stuff too. So all the information that's in there, unfortunately, you have to listen to me blab on there for most of that time, but there's a price to pay for everything.